Welcome to my channel. Today I'm going to discuss why the strong vacuum of space doesn't suck the atmosphere off of Earth when using the globe model for planet Earth. I recently heard a flat earther make the absurd claim that if Earth were a globe, the super strong vacuum of outer space would suck away all of our atmosphere. He viewed vacuum to be a very powerful force. This level of ignorance is troubling. But this is a common claim by the flat earth community experts, who seem to parrot each other's errors like a mantra. What is a vacuum? A vacuum is nothing. It is the absence of atoms. If you have a volume of space with no atoms at all, you have a perfect vacuum. This vacuum can in no way apply a force. There is nothing in it to hold energy or to create a force. It cannot, by itself, move even one molecule of material, let alone move the entire atmosphere of Earth into it. Let's take an everyday item that uses the concept of vacuum to do useful work, the common straw. How does a straw work? What is the mechanism that allows you to move a drink from a cup into your mouth so you can swallow it? Do you suck fluid up the straw? No, you do not. What you do is to create a seal with your lips around the straw and then use your muscles to create a volume of space in your mouth where the pressure has been decreased. However, there is another part to this system. The other end of the straw has to be inserted into a fluid, and the fluid has to be exposed to the air of the room. As you decrease the pressure on one end of the straw with your mouth, air pressure pushes the fluid up the straw because there is less pressure at the top of the straw than at the bottom. In the early years of my life, straws were made of paper, and if I drank a milkshake through a straw, the straw would often collapse because the air pressure on the side of the straw crushed it. The force it required to move the shake up the straw was more than the force it took to crush the straw. I was very happy when they finally invented the plastic straw, which was more robust. In any case, the actual force that moves something through a straw is not vacuum created by your mouth, but air pressure pushing on the cup and its contents. In the same way, the vacuum of outer space does not exert a force upon the atmosphere of Earth, any more than opening a door to an adjacent room to your lighted room will suck the light out of your room, no matter how dark the other room is. Darkness is not a force. And in fact, it is not a thing at all. It is the absence of a thing, light. Many years ago, when I was in the Navy, we used to joke about devices we called dark suckers. These were commonly known as light bulbs, but we would pretend that they were not emitting light, but rather were sucking all the darkness out of the room. It was a joke because it was so silly, so clearly wrong. We knew better. However, many people do not realize that air pressure and vacuum have the same relationship to each other as light and darkness do. There is no such thing as vacuum per se, but rather it is an absence of, or more commonly a decrease in, gas pressure. How does a vacuum cleaner work? Does it suck up dirt? No, it doesn't. To be more accurate, this device is an air motion cleaner, because it is the motion of air molecules provided by the ambient air pressure in the room that does the actual cleaning. The device moves air molecules from an internal volume of space and blows them out the back. This lowers the pressure in that part of the cleaner, and the now higher pressure of the room pushes into the mouth of the vacuum, dragging dirt, lint, and other unwanted things into the vacated area. Usually, the dirt is trapped in a bag for emptying later, and the air which has actually done the work simply passes right through the vent at the rear, maintaining the lower pressure inside the cleaner. If you were trying to clean the floor inside a vacuum chamber with no air pressure around you, the vacuum cleaner would not work at all. So it is obvious that the vacuum of outer space is neither powerful nor can it exert a force to pull our atmosphere away, even if it were a perfect vacuum, which it is not. But why doesn't air pressure push our atmosphere into space the same way it moves air through a vacuum cleaner? Gas molecules move quickly, but do they move fast enough to get into outer space? Generally, they do not. Escape velocity for planet Earth is 11 kilometers per second. That is over 25,000 miles per hour, or nearly 33 times the speed of sound. Any object moving away from the surface of the Earth at a slower speed than this will not get away, but instead will either fall back to Earth or enter an orbit around the planet. If, for example, you fire a gun straight up into the air, the bullet will simply fall back to the ground. Since it will arrive at the ground going almost the same speed as when it left the gun, this is, of course, a very bad idea. You could injure or kill someone if he gets in the way. Hydrogen atoms, at room temperature, are on average moving very fast because they are so light. Their average speed can be around 1,750 meters per second or 1.7 kilometers per second. Since the range of their speed falls around the average in a bell curve, that means that some of them will be moving much faster and they can attain escape velocity. We do lose a few of them to space. But velocity is a vector quantity, meaning that moving fast enough is not all you need. You also need to be moving in the correct direction, away from Earth. And perhaps the greater problem a molecule will have if it attempts to escape its prison are the other inmates. The average travel distance, or mean free path, that atoms have at 1 atmosphere of pressure is around 65 nanometers. If you remember my scale, Why You Don't See the Curvature of the Earth video, you will know how truly tiny such distances are. If an atom is moving fast enough and heading towards outer space, it will only get far enough to where it would take an electron microscope to measure the distance it traveled before it hits another atom and gives up some of its energy, and that will slow it down. To get from the surface of the Earth up to outer space is nearly impossible, and that is why it very seldom happens. By the time atoms reach the top of the atmosphere, they nearly always have given up enough of their energy to fall short of actually escaping, and so they fall back to Earth. We should all know that there is a pressure gradient in our atmosphere. For nearly a century, airplane pilots have used this fact to judge their altitude very closely, because as altitude increases, air pressure decreases in a known and repeatable fashion. The altimeter was invented in 1928, the year after my father was born. This makes perfect sense for anyone who has gone into the deep end of a pool at 9 or 12 feet and swam down to touch the bottom. You can feel the pressure increasing as you descend. The pressure goes up because there is more and more water above you pressing down. It is like stacking weights upon your chest. Each additional weight makes it harder to breathe because the force of all the weights is cumulative. There are miles of air above us, pressing down upon us, creating a force of 14.7 psi on every square inch of your body, as well as all the other objects on Earth. This is enough force to crush large metal objects like railroad tanker cars or 50-gallon drums. You only have to seal the empty container and then pump out all of the air from inside. Air pressure will do the rest, crushing them like an empty aluminum can you crush in your hand. As you ascend in the atmosphere, just like rising through the water, the pressure around you drops because the amount of air above you pushing down is less. By the time you get up near the point where you would call it outer space vacuum, you would find the pressure will be exceedingly small, with only a very few molecules still around you. The air pressure caused by these few molecules is so tiny that it is not enough to overcome the pull of gravity, and therefore they remain trapped inside our atmosphere. In summary, there is simply no such thing as a strong vacuum. All they mean by the term high vacuum is a vacuum that has had a very high percentage of the molecules in the area removed. A vacuum exerts zero force. It cannot pull things into it, not even a single atom. All it can do is provide a nearly empty space where pressure from outside of it can force material into it easily. If you enjoyed the video, please click like, and if you haven't subscribed yet, please do. If you click on the bell, you will also receive notifications when I put up a new video. Thank you for watching, and I'll see you next time.